All right, now in chapter 13, we talked about vector valued functions. R of t, think of that as a curve is traced out in R3, and the position vector for the point on that curve is what your vector valued function is. It turns out the components of the vector valued function are precisely the precisely the parametric equations for the curve. So, for example, let's see. Suppose you want to find the curve of intersection between these two quadric surfaces. Well, you could, in this case, it would probably be easier to let x equal t, y would be t squared, and then z would be 4t squared plus t to the fourth. Here, you're trying to find the parametric equations for the curve of intersection. I'd be tempted to set the two z coordinates equal to each other and square both sides. The y squares cancel. So that suggests letting x equal t, y equal t squared minus 1 over 2, and then z would equal 1 plus y. Let's see, and in addition, this particular example in 13.2 is really important. It should have been a theorem. It says that if a vector value function has constant magnitude, then r will be orthogonal to r prime. So for example, if this is the unit tangent vector, and this is the unit normal vector, you can tell that t is orthogonal to n, because t has constant magnitude. So t is actually orthogonal to t prime. And n is just the unit vector in the direction of t prime, so they are orthogonal. You should know how to use the arc length formula. For curvature, it's defined to be the rate of change of the tangent vector, the unit tangent vector with respect to arc length. Much easier way to compute it would be it's the magnitude of t prime over r prime, but this is probably the easiest one. Use this formula because you don't have to find t prime for that. We talked about the derivative function. If you look at the difference quotient, remember the vector from p to q is the difference r of t plus h minus r of t. So when you divide by h, you get a vector in the direction of that, maybe a little bit longer perhaps. But as h gets close to 0, this vector pq gets closer and closer to the tangent vector. So that's how we define r prime of t, the limit as h goes to 0 of this. And r prime will be tangent to the curve. The speed is the magnitude of the velocity, which is the magnitude of r prime. Acceleration is the derivative of v, which is the second derivative of r prime. We also talked about the binormal vector. The binormal vector is t crossed with n. And we talked about the normal plane. The normal plane is easier to find than the oscillating plane, because for the normal plane, t is your normal vector, but for the oscillating plane, you'd have to use b for your normal vector. We talked about the components of the acceleration can be written in terms of t and n. The tangential component has to do with the change in speed. So if a particle is moving at constant speed, the tangential component is 0. This is the easiest way to compute it. Whereas the normal component has to do with how much curving the path involves, and the speed at which the object is moving. This is the easiest way to compute it. Then in chapter 14, we talked about functions of several variables. Now, the idea is your domain element, xy, can be thought of as a point in the xy plane, and the z value, the function value, can be thought of as the height of some surface. But not every surface is a function, of course. For example, a sphere is not a function. All functions of several variables are surfaces, but not all surfaces are functions, right? Anyway, so here's an example of a function of x and y, and it might be easy. A helpful way to graph it would be to pick certain values of z, call this z, and you would find you can graph the level curve in R to R2, and you can graph several of those and see what the graph looks like. If you let this equal z and you square both sides, what you'll see is this is actually a hemisphere, isn't it? And that's what this suggests. We talked about a limit. As xy goes to ab of f of xy equals L. What is the definition? Well, the function value L, f of xy, can be made arbitrarily close to L within L minus epsilon and L plus epsilon by picking a delta, which is the radius of a circle around AB, so that if xy is any point in that circle, then the f of xy, or the z coordinate, will be between L minus epsilon and L plus epsilon. Now, to compute the limits can be kind of a challenge. it's actually easier to show that a limit doesn't exist than it does. This turns out not to exist because if you pick a path along y equals 0, which would be the x-axis, you see that your limit is actually, it gives you 0. But if you pick a path along the y-axis, which is x equals 0, then you get -2. So since you found two different paths, which give you different values for the limit does not exist. This one, you could try the same thing with this one. You'd find all the paths you choose, the limit's getting close. It looks like the limit's 0. How do you prove that it's actually 0? Well, that's a little harder. You could appeal to the definition, or the squeeze theorem is oftentimes helpful. Of course, the best thing to know is if it's a continuous function, then the limit exists and it equals the function value, right? At 0, 0, this function is not a continuous function because it's not defined there, but the limit still might exist. The function is greater than or equal to 0, and it's less than or equal to this because cosine squared is always between 0 and 1. And then the x to the fourth makes the denominator bigger, so this is smaller than this, and this equals 5y squared. So this goes to 0, this goes to 0 by the squeeze theorem. The function goes to 0 also. So for the definition of a continuous function, a function is continuous at a point. First of all, it has to be defined there. Secondly, the limit has to exist. And thirdly, they have to be the same. 1 has to equal 2. So this is a good example of an example where a function is defined as 0, 0. In fact, it equals 1 there. The limit exists. We actually just showed this limit's 0. But since they're not the same, we say it's not continuous at 0, 0. It would be continuous everywhere else, though, right? Okay, we're doing pretty good here. Let's just finish this up. The last thing we talked about was partial differentiation. The idea is the partial derivative of a function with respect to x, you keep y fixed and you look at it as a function of just x. The partial with respect to y, you keep x fixed and you look at it as a function of y. And anyway, and so you could talk about the second partials as well. Let's look at a couple examples. Here's my function, and I want to find this. This is actually, you first take the derivative with respect to v, then you take the derivative of that with respect to u, then you take the derivative of that with respect to u. That's what this means. So here we go. What's the derivative of this with respect to v? This is to the 1/2 power, so it's 1/2 this expression to the -1/2 times the derivative of what's inside with respect to v. That'd give you a 2v, wouldn't it? So there you go. That's dw dv. Now, if you take the derivative of that with respect to u, we're looking at v as a constant. So the v factors out. It's a constant. And we're taking the derivative of this with respect to u. So you get -1/2 u plus v squared to the -3/2. But the chain rule, you got to take the derivative of what's inside with respect to u. That's where we pick up a 1. So this is the derivative of this is d squared w du dv. Now, we one more time, we take the derivative of this with respect to u again. V over -v/2 is a constant, so it factors out. You bring this down, you get 3v over 4. Take the derivative, it becomes u plus v squared to the -5/2 times the derivative of what's inside, which is 1. So there you go. One more. Let's see. So if you have this function here, you can use implicit differentiation as well. I want to take the derivative of both sides with respect to x, and I want to find dz dx. So what's the derivative of this first term with respect to x? Well, remember, y is held fixed, so it's just going to be y times dz dx. What's the derivative of this with respect to x? Well, remember, ln y is fixed, so you factor that out and take the derivative of x with respect to x, so you get 1. On this side, you're going to get, so we're assuming z is a function of x, so it's going to be 2z times dz dx. To finish the problem, you just have to get all the terms that have dz dx on one side, factor out the dz dx, and divide. And that's it. And good luck on the final, everybody.